Okay, so good morning. So today we will study a very interesting uh, take on the simple pendulum, which is the Foucault pendulum. So what is this? It's just a fairly long. Okay, so long means at least maybe length is around maybe of the order of tens of meters, or maybe 10 to 30 meters. Okay, it's fairly long, and we will still stick to simple small oscillations. Okay, then omega is just root L by G, and so this is order 1, because if L is around 10 meters and G is 10 meters per second square, just to estimate these numbers, so it's order 1. Okay, omega, we'll call this omega naught. Sorry. Okay, so this simple setup can be used to do several things to show that one, Earth is in a non-inertial frame. Okay. The second thing is you can measure latitude. Okay, so this is what this is uses of it, and so at IITM there is a big building called the ICSR building, and it has a nice atrium entrance. It has a very nice entrance. Someday when you come to campus, you will see it, and I hope that someday we'll have one there. We don't have one there. Okay, so this is my wish list. Okay. So it's a fairly big building, so you put at the top of the building and you let it down and you let it oscillate. Okay, so let us so numbers are important, and I asked you to compute some. In the next problem set. Okay, so the point here is, first thing is that one thing we know is that the centrifugal term can be absorbed into a G effective. Okay, and this correction term is proportional to omega square R by G. Okay, where omega is Earth's rotation, angular velocity of Earth. Okay, so what will be the angular velocity? It will be 2 pi, right? 2 pi in how many hours? Around 24 hours. Okay, so 1 hour is 3,600 seconds. So this is what would be omega. So you can see that omega is a fairly small number. Okay. But what is R? It's around 6,400 kilometers into meters. So this is in meters, right? So you plug all these numbers in. Okay, and so you will see that this is of the order of 10 power minus 3. Okay, so that's It is small, but it is it's not. Yeah, so let's leave it at that. And we can also see what about omega by omega naught. So omega naught was order 1. So omega by omega naught. So this is dimensionless, by the way. Okay. And omega by omega naught, which is omega naught is the period of that thing. That's another dimensionless guy. And this will be, you look at this, so 2 pi's will cancel, etc. So it's of the order of 10 power minus 5, I think. 1, 2, 3, 4. 1, 2, 3, 4. It's around 10 power 4 or minus 5. Okay, I'll just write it approximately. Okay, so you can see that omega by omega naught is 100 times or whatever it is, at least less than omega square by g. Sorry.
Sir, omega naught is for the pendulum?
Yeah, simple pendulum. I defined it just here. Okay, so L is of the order of 10 meters and G, we are just doing order of magnitude thing. Okay, so omega square R by G is larger than that. Okay, but we want to, so I just want you to see that there's a dimensionless guy in the story. So these are order of magnitude things that we want to do. But the deflection of the simple pendulum of small oscillations will be much smaller. Will be, by that I mean, how much it's going to move in the x direction. If it is like this, it's moving this way, small oscillations, it's going to be fairly small. Okay, so, and for that, I just want to, let's say that deflection, we'll call it, say, capital A. So omega square A by, A by G will be much, much less than omega square R by G, because A will be of the order of mm, say, when R will be is of the order of kilometers, 6,000 thousands of kilometers. So obviously this is much lesser, but you can actually see that a little bit of thought will show you that this will be even smaller than. So there's a hierarchy. These are the things. Okay. So this we have to keep this in mind. You can put in numbers if you want and just put it. So it's easy to see that this is the hierarchy. Okay. So first point is that we cannot neglect this first, but we already saw that this can be absorbed in a G effective. Did I mention that? Yeah. Okay. So it can be absorbed in a G effective, and so there will be a so the vertical as given by a stationary pendulum or plumber's line. Okay, plumb line is nothing, right? The plumber will want to get a vertical, right? So he'll have a heavy object with tied with some twine and hold it, and if it's not moving, it'll give you the vertical. Is not the same as a radial direction. Which we define to be on Earth, right? On the local system as E3 prime. Okay, so this is important. I mean, so we could proceed as follows. So you can be very, very precise, and we can define E3 double prime to be the real vertical. Okay, so if you want a formula for it, this will be that cosine theta t E3 prime, I think, plus, suspect it is plus sine theta t E1 prime. So we can define that, and yeah, so that is E3 double prime. I have defined that, and then E2 double prime will be just E2 prime. Okay, that nothing happens, which was equal to also E hat phi, right? And then E1 double prime will be E2 double prime cross E3 double prime, just using the cross thing. And you can work this out. It is just cosine theta t E1 hat minus sine theta t. Okay, so this would be, so what I want to say here is E1 double prime, E2 double prime, E3 double prime will be the natural orthonormal basis chosen by a person on the surface of Earth. Okay, is this clear?
Sir, you said that E3 dash cap is not as same as radial direction.
Yeah, E3 prime is. But E3
okay,
prime was.
Yeah, okay, so E3 double prime is not same. Okay, I get it.
Okay, and actually if you go back and compare theta t, tan theta t is roughly proportional. It depends on omega square r g, and there is some sine theta cos theta, but it depends. So it's 10 power minus 3. You can see that it's a small. Okay, so theta t is small. So okay, but nevertheless, what I'm trying to say is that so a person who locally you want to choose coordinates, so I'll put prime to remind you that that is a coordinate. This would be x E1 double prime plus y E2 double prime plus z E3 double. This is what would be a point on the surface of the Earth where we assign. If we say that the floor of the thing is 0, where we are standing, whatever, have some 0 chosen, and then, right, then these would be the coordinates, right? I just want to, you can go ahead and use this. And now we can go, so now we are ready to discuss the case of the Foucault pendulum, and we have to put in the various forces. So, okay, so, and G effective will be, minus some G times E3 double prime.
But sir, the primed coordinates were also like, 2 were parallel to the 2 were in the plane, in the local plane along the surface of Earth, and 1 was perpendicular to it in the radial direction.
Yeah.
So
yeah, but that is E3. Yeah, that's how we chose E1 prime, E2 prime, E3 prime. Okay. But what I'm saying is that what we would naturally choose if you were on the surface of the Earth is this. Because otherwise, there is this huge part of the centrifugal force has 2 parts. One which is omega cross r. Okay, but that's a constant depending on, once you're on a point on Earth, that is some constant vector, right? So that vector will behave no different from G. I mean, you can't separate them out. You can't undo it, right?
Yes, sir, we can't.
Okay, yeah. So that's what I'm saying is that fellow is this guy, G effective. So if you're going to measure G, so if you're doing a simple experiment, let's ignore Coriolis, okay, for a moment. We will put Coriolis into the story. If you just ignore, if you didn't do Coriolis, or if you just try to measure G in any experiment by a simple pendulum, you will measure G effective. You're not going to measure the G, which is, right?
So we are defining new coordinate system, new unit.
No. We are only interpreting what we will naturally choose.
Okay. So right? That we can align G effective in there.
Yeah, exactly. Yeah. So what I'm trying to say here is that once we have done this, we can forget about this omega square r by G. No, that's all gone.
Yes, sir. Okay.
Okay, that's all I'm saying. Okay. So now, but that still remains. So the other terms that are there. are, omega cross omega cross, this x prime. This is non-zero. This is also part of the centripetal force because it's at some larger distance, right? This is also the centripetal force, but this is small. Already we saw omega, so this is of the order of omega. We want to compare with g, okay? Omega, this will be order omega square, and a is the deflection by g. So g times, I want to compare it with g or whatever. Okay, so this is of the order of this. This is very, very small and can be neglected. This we will neglect. Okay, compared to actually Coriolis force, to the Coriolis term, which will have only one power of omega. So this is this hierarchy. Okay, so we have this hierarchy. This we have taken care of. This is very, very small, so I throw it. So I want to only look at this effect. This is for Coriolis. We will see this in a moment, that the Coriolis force will actually be proportional to omega, that we know. But what is the constant in that thing problem is omega naught. Okay, so just to see, in most of our pedagogical physics courses, we actually do things exactly. And here is an example where I'm not going to do things exactly. Okay, because there is a hierarchy of scale. Also, many problems are simple. There's only one scale in the problem. Here we are seeing that there are multiple scales in the problem, and so now you need to ask what is the situation which is relevant for us, and then work on that. Okay. So is this clear why I'm going to throw away this term? This term is there. I'm not saying it's not there, but I'm saying it's going to be very, very small. Is that clear?
Yes, sir.
Okay. So now the problem is now centrifugal term has been fully taken care of. Has been taken care of fully. Actually, my English is also getting bad. Okay, so we will now study the effect of the Coriolis term. Okay, so let me now draw a picture. Okay, so in this picture, this direction, upward direction, will be E3 what? What will be this direction?
Double prime.
Double prime. Thank you. Okay, and then we have a pen. So, and then we have, so the other two planes are like this. Okay, so we won't worry about that. So let me draw one more line now for the pendulum and maybe use a different color. Okay, so this has length L, and let's call this angle alpha. Okay, so we have a tension which goes like this, mg, which acts this way. So these are the forces which act on this. Okay, so what we get is, so we can so let me first do okay, and we are going to assume that small oscillation, so alpha is much, much less than 1 is assumed. Okay, so in this case, so it's small oscillations. Okay, so there's another approximation I want to do, which is again a very good approximation. Z dot, which is the velocity in the z direction, will be much, much less than horizontal guys. So x dot and y dot. Is this clear? If it's small oscillation, it's very easy to see that virtually it's moving only in the horizontal directions, right? So horizontal velocities are much larger. Okay. Is this clear? This point, is this clear?
So this G is G effective actually, right? We are
Yeah,
just
exactly. Yeah, absolutely.
okay.
Thank you. Yeah, so I will not keep putting G effective here. If I forget also, it is G effective. Okay, thanks. Thank you. Okay. So let us now do the equation in the Z direction. So we need to do one more computation, right? So we need to do omega, so 2 into omega cross the velocity, right? So that is x dot this is what right? So we can just go ahead and evaluate this. Okay. So let me just write some equations and then, okay, so let's do this. So this would be the Coriolis term. Okay, so balancing forces. So what we will get is T divided by M plus G effective. This should be equal to acceleration in this setup. Okay, this order omega square is basically to take care of the term which you threw out, the centrifugal barrier. Okay, so let us do some balancing. Okay, so now we look at this in the Z direction, and yeah, so if you look in the Z direction, so T, so this will be T cos alpha. Correct. So this is the usual. Equation in the Z direction. But let's look on the X and Y direction. X and Y direction. X direction and Y direction. This is the more interesting guy. Okay. And so I need to do some calculations and okay. So first, yeah, this is correct. And since Z dot is small and alpha is also going to be small, we're going to assume even this we can neglect. And so we can say that T cos alpha to leading approximation is equal to G effective. Plus there are terms, okay, plus corrections, but this is good enough for our use, okay. So we need to work out what the equations are in the X and Y direction. So let me just write the equations. So I need to compute omega cross X dot. Okay, and I will be a little bit cavalier here. I won't distinguish between prime and double prime, but we can fix all those things. Plus y dot E2 prime. Okay, this I will compute, not double prime. Okay, so just being careless because I don't want to write a new formula for careless with double prime. Because the major effect we have taken care of. Okay, So there is nothing, I mean, for only E1 prime. So I'm just saying that I will just say that to leading order, I'll take E1 double prime is the same as E1 prime, which is not exactly the thing because theta t is small. Okay, so let me do this. So if you compute this, you will get minus omega sine theta y dot T3 prime plus omega x dot cosine theta T2 prime plus or minus omega y dot sine cos theta E1 prime. Okay. So you see, so let's forget for a moment. We'll come back maybe at Z or maybe we can discuss it later. If you look at the components of the Coriolis term along E1 and E2, you see that you get something like this. So what we get is T by M, its component along E1 prime will be equal to X double dot plus minus omega 2 omega y dot cosine theta. So I should put a 2 somewhere. I keep forgetting 2. Okay, this is okay for this computation. But there's a 2 in the Coriolis term. Similarly, T dot M this is what we get. Okay, and then if you use the small angle approximation, the left hand side, we get nice equations. You can just write this. You get minus G effective by L into X equal to X double dot minus omega y dot cosine 2 omega cosine theta and minus, this actually, restoring force is proportional to the displacement, right? That's what this thing is. Okay. So this we get nice coupled set of equations which we have to solve. Okay, but omega naught square is equal to G effective by L. Because omega naught is what we will measure. Okay, so we can replace this fellows by omega naught square. So let me actually do that in this equation. Is this clear what I have done? So now we want to solve this, and I will solve it in the following way. I will say U equal to X plus I Y, where I is square root of minus 1. Okay, it's just complex things. And then this equation nicely combines to become a complex equation whose omega square U is equal to U double dot plus I omega U dot cosine theta. Okay, where does the I come? Because X dot. Okay, so this particular term will come that way. Okay, so and this will be a 2. So we need to solve a nice equation which I will write in a different color now. U double dot. Can you see the red color?
Yes, sir.
Yes.
It comes out clear? Okay. So this is the equation that we need to solve. Okay. So let us do it in the following way. So now let me just go back to regular color. Okay, so we need to solve this equation. Okay, so let us do something like this. So let's make an ansatz. Say u is some u naught. U naught can also be complex. Okay, e power I gamma t. Then we can do u dot will be I gamma u naught e power I gamma t, and u double dot will be minus gamma square u naught e power I gamma t. Okay, so now we can plug this into that. What this does is we will see that this will become, and so here we have to solve a differential equation. This differential equation will become an algebraic equation for gamma. That's what will happen. Okay, so if you put that in, so what does it say? Wherever we see u double dot, so this is equal to minus gamma square u. This is equal to I gamma u, and this is equal to u, 1 times u. Okay, so we look here, u double dot, you write as minus gamma square into u, but I will write it like this, 2I omega into I gamma, and what's the last one? Plus omega naught square. Okay, so this equation, this is what we get, and this has to hold for, and u should be non-trivial, right? So when can that happen? When gamma square solves this equation. Okay, so implies minus gamma square, this will become minus 2 omega cosine theta gamma plus omega naught square should be 0. Is this fine? Do you understand? This equation has to hold. And for u not 0, u is not 0. Otherwise, if u is 0, there is nothing going on, right? There's no deflection. We know that's not true. We have to solve this. And so we can solve this a quadratic equation. So we can just write this q gamma equal to this minus is correct, no? Was there a minus sign anywhere else? Okay, plus 2i. This is correct, no? Plus 2i. So that will be minus b square plus okay, is this fine? So this is what we get, and so there are two solutions. Okay, corresponding to both choices of signs, and so gamma plus is clearly greater than 0, right? Do you agree? Gamma plus is greater than 0, and gamma minus is less than 0. Some negative thing.
So
yeah.
In gamma it will be 2 omega cos theta, right? Like minus b, so b is greater than minus.
Which?
The quadratic solution which you have written.
This one is this. Yeah. Have I missed something?
A is negative, Bidhi.
See, no. Or I can do it this way: plus, and put a minus.
I missed that. Sorry.
Okay. Yeah. No, I make mistakes. Don't worry. Don't feel sorry. It's okay. Okay. So these are this is what we get. So the most general solution is u equal to a e power I gamma plus t plus b e power plus I gamma minus t. This will be the most general solution. Okay, so first thing we'll do some limits. Is this clear? And A and B in general will be complex. And so, okay, so this is the thing. So first thing is limits we will do. First limit is take omega to be 0. Okay, so then what happens? If omega goes to 0, that means Earth is not rotating. Then gamma plus and gamma minus go to plus or minus omega naught. Okay, so that is the usual, oscillations, right? The usual oscillating solution. That is good. Okay, now we can do the case when omega by omega naught is much less than 1, which is our case. Okay, we can do this, and so what we get is in this case is that so coming back to this, so what it says is this term is much smaller than this, so we have to pull out, so we have to look at gamma would be minus omega theta plus omega naught square into 1 plus 4, what was the b term, 4 cos theta. Okay, so this will become sorry, I have to outside the square root, so this becomes omega naught. Now it makes sense dimensionally. Okay, so this, so for leading term is plus or minus omega naught. Okay, and now we get the next term in this would be minus this is what we get. Okay, so the dominant term is going to be these two terms only. Okay, so if you want, we can even neglect this because this is going to be even smaller. We saw that omega by so again now you can see why we computed omega by omega naught earlier. Okay, so now we can write our general solution. U will be e power minus I omega t cosine theta times okay, so you can see when omega, this is the standard solution. When omega equal to 0. That is when an Earth is not rotating. Okay, so let's choose some initial condition. We have to now A and B are fixed by initial conditions. Okay, so let's say that at t equal to 0, okay, x was some constant, so we'll just call the used up A and B. Okay, so C, this is some real constant. Okay, x dot is 0 and y is 0, say, and y dot is also 0. So what we have done is we are starting the pendulum with a displacement of c in x, okay, and letting it go. Okay, so we can go ahead and do this computation. Okay, and so what we will get if you put that in at t equal to 0, if you do this computation, and we'll also, so one more thing here is, you have to remember that omega is much less than omega naught. Okay, so this you can see, so there are two frequencies in the problem, omega naught, which is much faster than this omega. Okay, so we can simplify things a little bit, and we can write u. Okay, so let us just write something. U will be some c times e power minus I omega cosine theta t times, say, cosine omega t. If we do this, okay, you will see that I suspect that these boundary conditions will be satisfied. But if you ask, oh, I could have put y equal to something else, and then that we can take care of by putting some phase here in the argument. So this is what is going to happen. So now let us ask what is happening. So what does this mean? What does this term do? Okay, so let us look at our, so when omega equal to 0, the pendulum for the chosen initial conditions oscillates in the xz plane, right? It's like a standard thing. You just do this thing and you let go. It'll keep going into this thing. There's nothing else. But what is happening is that because there is a Coriolis force will push it along the y direction. That's what it's going to do, and it'll start. Okay, so omega not equal to 0 implies the plane of oscillation of the pendulum recesses. Okay, so I want to draw a picture here. So let's say this is the z direction. So that is a plane of oscillation. So this is, okay, and so let's draw something. So this would be some x and y, and so this will precess. Okay, that means this plane will start rotating with frequency. With what frequency? Anybody?
Omega cos theta.
Which is also omega sine latitude. Okay, so what is going to happen? So you can see that this is a small. We saw what was omega. Omega was some 10 power minus 6 or something, minus 5, minus 6 or some small number like that. Okay, so the thing is that it will change by a very small angle in a given day. Okay, but you can see that happen. You can actually see it precess. Okay, and L is latitude. Is this clear? So this is so you can see that the precession frequency is determined by latitude. So if you can measure the precession frequency, omega we know it is just the time period of Earth's rotation, and then okay, so the idea here is that I want you to go ahead and put all these things and compute these numbers. Okay, so one more thing you should do is go back here and put this in that thing, and you should find that it does not solve that equation. Nobody pointed out this should be omega naught t. Okay, so this is actually plus order terms which you have dropped of the, or which will be smaller by, you know, some order omega by omega naught or something, you know. So yeah, exercise, bunch of exercises. Okay, compute the precession frequency for Chennai. Okay, check that our solution u equal to some a e power, what is it, minus I omega cosine theta t into cosine omega naught t plus some constant, so I'll put something here, plus little b maybe. Okay, b is a constant. Almost solves the differential equation approximately only. Okay, there should be terms, there might be terms that are suppressed by some small number like omega by omega naught. Okay, so check this. Is this clear what I'm saying? Okay, and and the last one is a nice exercise, an animation exercise. Okay, so you want to solve the equation. You plot the time evolution in the xy plane, of course, of the precession for two cases. Okay, that means you want to plot x of t, y of t, which solve the differential equation. Okay, for two cases. Okay, the second case is also when omega is comparable to omega naught. Suppose, okay, and you can animate. So what you do is you take snapshots at different times. You can combine them. There are things like GIF. You create separate GIF files or JPEG files and use some sort of like GIF anim or something like that to merge images into a movie. Okay, so please do this. This you should do. And the last part is, check the Z equations properly. Okay. Don't believe what I said. I did some approximation. So please check all these things. And so this sort of concludes what I wanted to say about Earth as this thing. I also want to give you a reference. This is there in this thing, but check out the chapter on non-inertial frames. In a book by Marian and Thornton. Okay, it's a BSc level book, but it's I think a very nice book. And he also uses formulae which raise my BP, but it's a beautiful book. Okay, so please play with these things because that's how we will discuss things. Okay, so thank you. So any floor is open for questions now.